So for that first one, we're taking a statement and we're adding an if and a then. So if an animal is a bird, comma, then it has feathers. So it wants me to identify my hypothesis in red. My hypothesis is that this animal that I'm observing is a bird. Remember, I did not underline the if, just the part that follows. My conclusion is, if that animal is a bird, then it has feathers. Now, these if-then statements may not always be true, and that will be important when we talk about if it's true or not. You are in Texas if you are in Houston. So how can I rewrite that in if-then form? If you are in Texas, then you are in Houston. Or if you are in Houston, rather. So this one was tricky. You are in Texas if you are in Houston. So notice that the if was after. So you want to ask yourself what makes the most sense here. If you are in Houston, comma, then you are in Texas. That makes more sense than saying if you are in Texas, then you are in Houston, because there are other parts of Texas, right? Dallas, for example. So my hypothesis is you are in Houston, and if you're in Houston, you must be in Texas. Does that make sense? Okay, basic logical reasoning. Questions? Anyone still writing? We're good. Okay. So we're looking at negations here, like I said. Note that the last slide, when we talked about conditionals, we typically write it like this. If P, then Q. That's logic notation. Again, if you take the LSATs, if you go to law school, if you take a logic class, you learn this. So if P, then Q, that's called a conditional statement. P being your hypothesis, Q being your conclusion. And then as soon as I place a little squiggly in front of the P, or you may see it like this, either one, that means not P or not Q. That's negating that statement. So the statement is the ball is red, the negation is the ball is not red. When we do proofs in geometry and we're going to be given something and we have to follow a sequence of logical deductions to make some sort of conclusion, this is what we're going to be doing. Looking at negations, looking at conditionals. The cat is not black, so the negation would be the cat's black. Questions on this? Anyone need more time on the slide? All right. So we have our conditional, our just plain old if-then statement. If you're in Houston, then you're in Texas. Now, we have the converse. The converse is just switching that around. If you're in Texas, then you're in Houston. Now, that may or may not be true. Sometimes both your conditional and converse are true. Sometimes one's true and the other's not. Sometimes they're both false. So that just switches your statements around. If you're in Texas, then you're in Houston. Then you have in inverse. Inverse is the opposite. That's how I think of inverse, and that's how I think of an inverse statement. So our original conditional was, if you are in Houston, then you are in Texas. The inverse is, if you are not in Houston, then you are not in Texas. Does that make sense? And then you have the contrapositive. And I'll most likely do some sort of note card extra credit thing with these words because there's a lot of them. The contrapositive says you're going to switch them around and you're going to look at the inverses. So, if you are not in Texas, then you are not in Houston. So in that case, that contrapositive and the conditional is true. Now, the common error says just because a conditional and its contrapositive are both true, just like the Texas statements, that does not mean that its converse and inverse are both false. The converse and inverse could also both be true. It just depends on the statement. Does that make sense? The hard part here is remembering the terminology. What does it mean to be a conditional? What does it mean to be a converse, an inverse, and a contrapositive? And on the test, I typically have a statement. I have you turn it into a conditional. I have you write the converse. I have you write the inverse. I have you write the contrapositive. Now, you don't have to write all this down here, but it says a conditional statement and its contrapositive are either both true or both false. Similarly, the converse and the inverse of a conditional statement are either both true or both false. In general, when two statements are both true or both false, they are called equivalent statements. So when we looked at the conditional, if you are in Houston, then you are in Texas, that's true. And we looked at the contrapositive. If you are not in Texas, then you are not in Houston, that's also true. So those are called equivalent statements. They mean the same thing. Does that make sense? Okay. Okay. Let's just look at A. How would I write the conditional? Yeah, if you are a guitar player, then you are a musician. That's right. That hypothesis, you are a guitar player. Conclusion, you are a musician. So, is that true? Oh, sorry, it's on freeze. Is that true? Yeah, I guess it depends on your definition of a musician. But yes. The converse of that would be what? Yeah, if you're a musician, then you're a guitar player. Is that true? No. I could be a flute player. I play the flute. What about the inverse? Yeah, if you're not a guitar player, then you're not a musician. Is that true? No. The contrapositive would be what? How would I write the contrapositive? If you're not a musician, then you're not a guitar player. So if we're just assuming that anyone who plays an instrument is considered to be a musician, then that's also true, right? And in this case, the conditional and contrapositive are true. They're what are called equivalent statements. Okay. Again, you will not always have the situation where A and D are true and B and C are false. Just depends. That a good definition, and you might want to write this down, a good definition is true forwards and backwards. So, all apples are fruit. That's not a very good statement for the definition of a fruit, because forwards or an apple, because you would say if a fruit is an apple, or if you have an apple, then you have a fruit. If you have a fruit, then you have an apple. That's not true, forwards and backwards, correct? So that's not a good definition. An apple is not a good definition for a fruit, and vice versa. If you can look at it forwards and backwards and say to yourself, that is true, then it's a good definition. All mathematical definitions are true as their conditional and their converse. If not, then it's not a good math definition. So if we think about perpendicular lines, it says, if two lines intersect to form a right angle, then they are perpendicular lines. If I switch that around and I said, if two lines are perpendicular, and sometimes you have to rewrite it, and that's the one thing in geometry that a lot of students don't like to do. You can rewrite it a little bit, but just to make some sense in English, right? So you could say, you don't have to say if you have perpendicular lines. You can say, if two lines are perpendicular, then they intersect to form a right angle. That's also true, correct? So that means that that's a good definition for perpendicular lines. Or you could say what they wrote. If two lines are perpendicular lines, if two lines are perpendicular, it doesn't really matter how you say it as long as you're saying the same thing. Then they intersect to form a right angle. Any questions on good definitions? All right. And remember, the notation for perpendicular is this. So L is perpendicular to M. Your teacher should have talked to you about that last year. Hopefully they did. That means they form a right angle. Let's look at this first statement. It says line AC is perpendicular to line BD. Note I use two letters to say that I have a line, not three. Some of you wrote 3 letters. You missed it if you did. And notice that I have double arrowheads. Some of you didn't put your double arrowheads. You missed it if you didn't. So, is line AC perpendicular to line BD? Yeah, right? Because they intersect to form a, what kind of angle? Right angle. So we just use that definition right away. So that is true. So when we do proofs, we're going to be using statements like that. We're going to say AC must be perpendicular to BD. Why? Our reason would be because they intersect to form a right angle. Does that make sense? That's how we do a proof. Okay. Angle AEB and angle CEB are a linear pair. Is that true? Yeah. Again, some of you on the test, this is how you note an angle, with the angle sign, not with the line above it. You use your vertex in the middle always. So angle AEB is this angle. Angle CEB is this angle. And by definition, they form a linear pair. So again, that's getting you ready for proofs. If I'm looking at a diagram and I'm trying to prove something, and it's important that I say in my mathematical argument that angles are linear pairs, then my statement would be, Well, they are adjacent angles that add up to be 180 degrees. That's how I know they're a linear pair. Every statement has to have a reason when we develop these mathematical proofs. Ray EA, and ray EB are opposite rays. So this was another misnotation one for some of you on the test. E is my endpoint. So EA is this ray right here, with the ray going forever in A's direction. E is the endpoint. EB are opposite rays. So EB would be this ray. Are they opposite rays? No, because opposite rays have to have points that are collinear. And it says that if E is in the middle of AC, then EA and EC are opposite rays. Right? But E is not in the middle of A and B, in the sense that we're looking at the middle of collinear points. Does that make sense? Okay, I will say this. We're going to start proofs this chapter. Proofs are by far the most difficult thing that a lot of students do in mathematics. So if you need help when we're starting to do these proofs, please make sure that you are an advocate for yourself and that you come in early for help and that you're watching these videos. Angle JMF. So I'm going to mark this. Always mark your diagrams. It's going to help you out in the future. JMF is this angle. FMG is this angle. I don't know if they're the same, so notice how I marked it with 2 arcs instead of 1. Are they supplementary? Yes or no? Yes. Why? They're a straight angle. That would be a good reason. You could say, well, straight angle, that's a good reason. So yes, that's true. That's correct. Point M is the midpoint of FH. Is that true? No. Does it show anywhere that it divides that in half? It kind of looks like it does. But kind of looks like and actually does are very different things. And a lot of things that geometry students do that are frankly bad habits is they look at a picture and say, well, it looks like a right angle, so it must be. Don't ever assume. That is your worst enemy in this course. So we don't have, if we had this, then that would be a different story. Then by those markings alone, I could make that conclusion. But I don't have anything on this picture to make that conclusion, so it's false. So we're looking at 2 other angles now. Says angle JMF, so let's mark that. JMF is right here. And angle HMG are vertical angles. Is that true? Yeah, that's true. We can assume that. Because their sides form opposite rays. They make that X shape. Line FH. So line FH is this line. Line FH and line JG are perpendicular. Are they? We don't know. No, they're not, right? Visually, because if lines were supposed to be perpendicular, we would get some sort of marking like this, right? And we could say that the 2 lines are perpendicular, but we don't have that here. So this is false. So notice, definitions are extremely important in geometry to make these mathematical arguments. This is the end of part 1. Do you have any questions for me before I go over your test? And my battery's low. Yes? No? So